Welcome back to another episode of Scientifically Simple. My name is Brandon. I'm joined today with Mo, and we're going to be looking at the what we'll call the puppet master, kind of the unseen force in Mother Nature, right? So when we look at like enthalpy and these other processes, we see that there is the ability to move from point A to point B, from state A to state B, etc., right? And it seems too easy. And that's not really what we see in our daily lives, right? We see that everything takes effort. It takes effort to take gasoline and burn our engine and move our cars. It takes not energy, but effort to make electricity, to power our homes and to work our appliances, right? And the reason it takes effort is because there's another element of thermodynamics we're going to talk about today, which is entropy, right? And entropy is kind of that other evil, the other side of the coin that has to be addressed. And it's essentially the cost of doing business, which we'll talk about more today. Mo?
Thanks, Brandon. Appreciate your introduction. That's very informative. So today we are going to be covering in our episode a quick recap on first law and the equation of state, second law of thermodynamics, and how the laws of thermodynamics evolved beyond the heat engines into the chemical industry. And from there we're going to be going through an example, just like address how like the first and second law comes together in our daily application, like for example in air compression. So as we mentioned before, in a closed system, internal energy is related to heat and work. Sensible heat is a function of temperature, with a specific here at constant volume called CV being specific heat. By simple substitution, we get that internal energy becomes a function of temperature, volume, and pressure. Then a new variable called enthalpy was defined to account not only for the internal energy of the system, but also energy required to move fluid into or out of the system. Which, as internal energy becomes also function of pressure, temperature, and volume. The next logical step was to ask, is there any way that pressure, temperature, and volume has any interdependency, or are they truly independent of each other? So, given we have an inner dependence between pressure, temperature, and volume, where defining two automatically define the third variable, both enthalpy and internal energy for a single component system can be a function of only two state variables, not three. That leads to construction of phase diagrams such as the one shown, which is like for ammonia. And despite being super intuitive, the second law of thermodynamics challenge is that we don't normally talk about entropy as a word in our daily conversation or news like we would normally do with energy. However, every time we see a clip with a cracked egg getting uncracked or milk flowing upward, we instantly know that the clip played backward in time, and that's the essence of the second law. Another perfect example, whenever we decide to be buying a car or a fridge, our decision will be based on how much gas mileage this car has or how efficient this fridge is. That's the question that centers around the second law, not the first law, because only in the second law we get to learn that different forms of energy, a car transforming chemical energy into mechanical energy, fridge is transforming electrical into heat energy. And that's pretty much what the entropy is the energy transformation law. And with the first law formula combined with work of Carnot, Boyle, Charles, Gay-Lussac, and Avogadro, Emil was able to analytically formulate the ideal gas law and consequently build the famous PV diagram of that cycle, consisting of the two isothermal and two adiabatic expansion compression steps. Then comes Clausius and makes a very interesting deduction by looking at Carnot's cycle. He sums up the heat flows across all the steps. Since two of these steps are adiabatic, then their values are zero. So the whole cycle heat values comes down to the summation of the two isothermal steps. Then he makes the two critical observations. The first one is no matter how many configurations or pathways to experiment Carnot cycle at, the sum of heat across Carnot cycle always have to be negative. The second observation was the higher heat always flows through the lower temperature level, aka the heat sink temperature always have the higher heat flow. So he deduces that the thermodynamic property that constrains the process efficiency has to be inversely proportional to the temperature, and it has to be negative or at best zero. He named the thermodynamic property as entropy, which for our audience it's actually a Greek word that means energy transformation, and that formulation came to be Clausius inequality for closed systems. And you may notice that the integral has a little circle in its operator, and that's because it's a path dependent integral, as the Q, as we mentioned before, is a path function. And that's the reason why we have an inequality, and practically means we have a feasibility region to optimize a given system.
Right.
And like we demonstrated on how combining an equation of state was first law to get enthalpy as a function of temperature and pressure, now we can be doing the same thing for the entropy as well, as we can see in the below diagram. And it's pretty redundant how we can actually build those diagrams. It doesn't have to be pressure, temperature, and enthalpy. It can be whatever two independent variables that you would like to have, and then put like the third dimension as whatever we want it to be. So there is nothing set in stones that it has to be only pressure and temperature.
And real quick, because it just dawned on me, for those of you who are a little bit unclear on what entropy actually is, the analogy that just dawned on me is the concept of no free lunch, right? So kind of to Muhammad's point, if every time we completed one of these processes there was no loss of energy, then there would be no need to refill our gas tank. There would be no need to regenerate our electricity. Nothing would be used, nothing would be lost. But the reality is every time one of these processes is fulfilled, a little bit is lost. And that is the entropy. That's where that comes in.
Yep, absolutely. So the second half of the 19th century was marked by a profound economic changes, such as the industrial transition from plants fueled by steam engine to chemical and electrical industry. This period saw the birth and growth of industrial chemistry. So far, Clausius' laws was originally formulated with engineeristic purposes to provide the heat engines technology with adequate theoretical tool. The theoretical path that allowed the second law to be embodied into chemistry took some decades, approximately from 1870s until the 1910s. So now we are moving away from, like industrial revolution, and we are moving almost to that realm of the almost like a brink of the First World War. So industrial revolution offered a significant leap to the human civilization, but was a heavy price though. By the late 1800s there were three challenges: exponential rise in human population, uneven distribution of human population across the land meant that many people were now packed tightly into urban centers, intensive farming, and rapid urbanization. So the question became now how to create sustainable agriculture under these new conditions that put chemists on the spotlight, because new techniques of mass production of chemicals, especially fertilizers, now became a survival requirement. So Le Chatelier is best known for his work on his principle of chemical equilibrium. Le Chatelier in 1901 attempted the direct combination of the two gases, nitrogen and hydrogen, at high pressure and temperature in presence of metallic iron. But unfortunately, a terrific accident happened which nearly almost killed an assistant of his, and consequently he pretty much gave up on further experimentation. By now, we are marching into the First World War, and Ostwald invented a process to make nitric acid by oxidation of ammonia, which is for our audience, the nitric acid is a crucial chemical for production of fertilizers and explosives.
Right.
However, it didn't become industrially significant, likely due to the lack of an expensive source of ammonia yet. So pretty much everything right now is waiting on that. Less than 5 years later of Le Chatelier's failed attempt to be making ammonia, Haber and Karl-Bosch, or Fritz Haber and Karl-Bosch, were successful in producing ammonia on commercial scale. Near the end of his life, though, Le Chatelier wrote, I let the discovery of ammonia synthesis slip through my hand. It was the greatest blunder of my scientific career. So Ostwald, now going back to the cornerstone for Le Chatelier and Ostwald in this picture, they have recognized the main contributions to the extension of the second law and to the chemistry domain came from the American engineer Willard Gibbs. He began pointing out that the fundamental equation of thermodynamics can be created by combining the first two laws of thermodynamics. And that's pretty much
Right.
like you have the first law, and of course it's going to look like now it looks easy, but he pretty much took those two and combined them in a constant pressure system and came up with that a new state function, because enthalpy and entropy as of now are state functions. So by definition, Gibbs is going to be state functions because it's the mathematical summation of those.
Right.
And he found out pretty much entropy has to be negative or zero. That means Gibbs has to be as minimum as possible. It's always the reciprocal of entropy. So Gibbs initially was interested in improving steam, like James Watt's steam engine governor. That's all what he was looking into. And by analyzing its equilibrium, hence he was the first to be introducing the concept of thermostatics or an equilibrium. So Gibbs is the first one that actually doesn't want to be dealing with kind of motion or dynamics in thermal. He literally wanted to be hey, let's just freeze every state. And what he was envisioning, he wanted to be having this 3D model that you see there, where he can relate entropy, specific volume, and internal energy. Then he noticed that the internal energy and the specific volume can be condensed into enthalpy. However, the system was only limited to a given fixed composition. That's what everything that we have been doing so far is single component system. So he intuitively decided that the new function of equilibrium, to be general, it has to account for a change in composition. So pretty much he introduced the differential change in mass or mole. So Gibbs free energy he already know that the Gibbs free energy will be changing if the composition will be changed. So I will have a rate of change of Gibbs as a function of mole. So for that equation to be physically consistent, a molar function has to be included. That's why he had to be putting this Fn, because to make it physically consistent in terms of the unit.
Right.
So that function came later on to be known as the chemical potential. And that's how the chemical potential came to be around. It's literally because of it. So from that core, we be coming to realize that basically Gibbs free energy is the integrated form of the first and second law, and that's why the Gibbs free energy is always an indication if a given process or a chemical reaction or a distillation process, it doesn't have to be a chemical reaction either,
Right.
is it going to take it spontaneously, or am I gonna need to be adding heat, or I have to spend energy in order to make it go into the direction that I need? So pretty much you can it's like, you can always have an endothermic reaction, and you can have like kind of like the change in entropy is positive, and yet the system can be going into that direction because it's an interaction of the enthalpy and the entropy, and what matters at the end of the day is Gibbs free energy itself.
All right, so real quick, so that H is our enthalpy. So as we've said a few times before, that's kind of our currency to play with. The T cross with S, the S being our entropy. Now that we've discussed that, that's the tax we have to pay. So it's gonna sound a little bit goofy, but as long as the tax that we have to pay is greater than the currency we have to provide, the summation of those two is negative. The process is actually going to proceed spontaneously. I realize that sounds a little bit goofy, but
no, it's actually perfect. Sounds perfect. Yeah, I mean, like,
right?
If you look,
yeah,
and some references always like looks at Gibbs free energy. It's the maximum work, or it's basically the maximum work extracted from system.
Right.
And it makes sense because because if you look at the entropy, if you look at the entropy, which is a reversible process, that means ds would be 0, and pretty much you get to the conservation of energy of the first law.
Right.
Because you can't break that one. So anything that you can extract from a given process, it's going to be the contribution of the first law, which is going to have to be conserving energy, and how efficient your process is. So those are the two contributions that comes in.
Right.
So with that, we'll be like going into our industrial examples, and we are going to be like taking a pretty like simple example in our system. And as you can see, like taking an air compressor as an example here, with the given conditions, we have like suction conditions around like atmospheric pressure, 90 F temperature, and we are looking into the discharge pressure to be around 20 psi. So if we take that into perspective, the first law has to be conserved. So pretty much the enthalpy change will be equivalent to how much work you are adding and how much heat is being generated. The second law is going to be like saying your dq can only be 0, minimum. It can be 0 or more than that. And that's why like normally we always like have the minimum work to be getting from a suction pressure to a discharge pressure is at Q0, and that's pretty much like why as we mentioned, the Q can either be 0 or more than that. So, and that's why like every time we try to be like saying adiabatic efficiency of a compressor, we always go to the adiabatic. Why is the adiabatic? It's because it is the best perfect stage, not isothermal. Isothermal requires we have some kind of a heat exchanger between compression stages, so we are adding a new thing. But like to go into the elementary pieces, pretty much the Q can either be 0, which is a adiabatic case, or isentropic case, or more than that. And as you can see from the chart, all possible compression pathways will lead to increase in temperature. So for the air, every time we try to be compressing, no matter what happens, at the exit of that compression stage, the temperature will be increasing even when you have, of course, the adiabatic case. And the sad part about the chart that you can see there is that only useful mechanical work is the bottom side, which is around 38 BTU per pound. The residual, as you get more and more inefficient in your design, part of that mechanical energy is going into heat, and it just gets worse. And that's pretty much like what it means when you have like a compression heat is 0 and it only increases beyond that.
So I'm really glad you said that, because there may be a few people who are still kind of confused. I think enthalpy is kind of easy to follow. Most people talk about enthalpy pretty easily. Entropy's always been kind of that vague, really hard to grasp concept. Mo said it right there. So typically when we think about what,
I mean, like, so
no, you're good, buddy. I think you're gonna say it.
Where is that, like, the entropy factor, like, practically speaking, is coming from? It's coming from pretty easy part in the compression. when you are trying to compress a gas, for example, the rotor is moving at a given speed, the gas is moving at a given speed. However, the stator, basically the casing of the compressor, is zero. So you are basically, there is a differential speed between the gas and the rotor and the stator, and that creates a friction, and that's where the heat is coming from. That's why you need to be compressing the air, not only to get its pressure to be getting higher, but on top of this to overcome the friction within the machine that's already built in because of the velocity differences, or basically the momentum difference between the gas and the rotor and the stator.
Right, and so when we talk about entropy, where that really shows up is heat. I mean, from your car engine to your electricity, right? Once you use that energy, I mean, typically there's a little bit left over, but you're going to see a change in temperature. And that's why entropy is also kind of referred to as waste heat or waste energy. Because unfortunately, unless you're like at a very high temperature or you have a lot of heat, there's really not much you can do with it.
Yep, absolutely. I agree 100%.
I was just throwing that out there for anybody who didn't know what entropy really was.
And yeah, absolutely. Yeah, that's pretty much like in a nutshell where the entropy is coming from. It's like you in a perfect world, you would be like thinking every joule I'm spending in the compressor should be gaining potential energy for the gas. But unfortunately, in reality, that's happening inside the casing. That's static, it's zero, and the gas is basically has to overcome friction. And on the top of this, the rotor is moving at a whole different speed. So that's where, like, when you have like a traffic, for example, and you have different cars, not every single lane is at the same speed, and that's where the friction is coming between those layers and heat is being generated.
I think that air compressor is a really good example because it does show you all the effort you put into, say, compressing your air, and you get barely anything out of it in terms of real useful work. I mean, that is a staggering figure.
Absolutely. I mean, someone might be like thinking as well, like, hey, there is the isothermal compression. It should be better than both of them.
Right.
But if you technically look into it, you're gonna find the compression stage. Then you're gonna add the inner stage cooling.
Right.
It's true. The isothermal is going to be if you have more than one stage, or want to basically make the stages like you don't want to get to that bigger pressure issue. When you actually go into that direction, you are gonna find out that the compression work is reduced, which is true, but the overall entropy of the system is going to increase because you transfer that heat into a whole different fluid. In that case, it's air cooling or water cooling.
Yep.
So, and you are going to literally find the amount of Q that you have released from the system is equivalent to the compression heat. It's not gonna be. What you have done is like pretty much like you instead of like the compressor has to mechanically deal with that heat, I basically outsource the heat to the cooling system.
Well, it's like the IRS, right? Yeah. Like the government's always going to get paid. It doesn't really matter what you do; they're going to get theirs from somebody.
Yes, pretty much. Yeah, I mean, like, you can't. I mean, like in that concept, in that sense, the compressor might have a small free lunch, but like someone else paid for it.
That's exactly right. 100% right. Yeah.
That's pretty much And just like to be like summarizing everything so far, we had addressed today. Clausius is credited with defining the second law of thermodynamics. He named the new thermodynamic property as entropy, which was a Greek word for energy transformation, which is pretty much what it is. Global demand for the chemical revolution paved the way for the thermodynamics to go beyond the heat engines, as we have stated before the First World War. Gibbs played a monumental role in transforming thermodynamics to play a global role in physics and chemistry. And thank you so much for watching, and hopefully stay tuned for our next episode around chemical equilibrium, and potentially we're gonna just like address some aspects of statistical mechanics, and we can go dive deep,
Yeah.
dive deeper into what defines entropy as a macro state and what defines enthalpy as a macro state.
That is really cool. I'm actually excited for that.
It's fascinating how all these things came together, and when we actually start to be talking about that, the audience will be like, definitely everybody's gonna know this. Like, it didn't take a jump step from classical thermodynamics to quantum mechanics.
Right.
It was super smoothly transferred, and we are going to be like addressing how this came along, and it was a very logical to be going into that direction.
I'm really excited for that, and hopefully you're excited too. If you liked what you heard or saw, please like and subscribe, leave a comment, leave a review. I want to say thanks to Mo for providing this material and speaking us through it. If you're like me and you have a lot more questions than you have answers, you can always send us an email to sciencemadesimple@outlook.com, or leave a comment on our YouTube videos, or, I don't know, leave a review and leave your question in there. We'll take a look and get back to you. As always, this is Scientifically Simple.